Today we're going to talk about one of the topics in 3E. So as I mentioned at the end of last time, 3E covers products and quotients of vector spaces. But I think quotients are probably outside the scope of this class. So we'll just do the first half of 3E, which is on products of vector spaces. Okay, so the idea of a product is to take two or more vector spaces. Let's call them V and W for now. These are both vector spaces over F. And try to combine them into a bigger vector space. That's the whole idea behind the product of vector spaces. Okay, in some natural way. Now let me just remind you that we kind of have some notion of being able to do this already, and we'll compare and contrast once we know what a product is. So recall that if, say, U1 and U2 are both subspaces of a common vector space V, then we define the sum of these two subspaces, right? Which is a way to take these two subspaces, these two vector spaces, and produce a bigger vector space, and that the bigger vector space contained U1 and U2, right? So the sum, this was the set of all vectors like this, but the sum of something in U1 and something in U2. And this thing was a subspace of V. So this sum is a bigger vector subspace of V than U1 and U2, in that it contained all of U1 and all of U2. Okay, but in this definition, I need to be able to know, in order to form the sum, I need to know how to be able to add something from U1 to something from U2. Right, so this really relies on the fact that these are both subspaces of a common vector space, right? Because this addition, this is happening in V. But what if I have two totally unrelated vector spaces, right? I have a vector space V and a vector space W. There's no relation between them. There's no way I can define a sum like this, because I don't know what it means to add something from V to something from W, because they don't live in a common vector space. Okay, so this is some notion of combining two vector spaces, but it's different than we'll cover today. Okay, so this is defined not just for a pair, but actually any number of vector spaces over F. Let's say any finite number are F vector spaces. Then the product of these vector spaces, we denote it with times's, right? V1 times V2 dot 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 times Vn. Okay, so as a set, this is just the set of all ordered M tuples where Vi is in Vi for all I. Okay, so as a set, you just take all possible M tuples where you take something from V1, something from V2, something from V3, etc., and you just write them down next to each other. Okay, but this is as a set. I need something to tell you the addition. Okay, so the addition and the scalar multiplication are sort of just maybe the nicest thing you could ask for, which is they just happen component-wise. Right, so if these are two vectors from the product, that means that V1 is in V1 and W1 is in W1. Since those are in the same vector space, I know how to add them. And so you just define the sum of two vectors in the product to just happen component-wise, right? So this addition is in V1, this addition is in V2, etc. This addition is in the product. Okay, and scalar multiplication, you could probably guess, if you have a lambda in F, then when you scalar multiply an element of the product, you just scalar multiply into each component. And this makes sense because each of the VI's is a vector space, right? So this scalar multiplication is in V1, this scalar multiplication is in V2. That's the definition of the scalar multiplication in V. Okay, here I'm trying to point to the product part of it. Obviously the scalar is an F. And this makes the product into a vector space over F. So I'll just state this without proof. Okay, so in other words, addition is commutative, associative, scalar multiplication has all the properties that we discussed on actually the first day of class. This is basically the most straightforward way to put two or more vector spaces together. Right? All you do is you just write the elements next to one another. So, concrete example. Okay, let's take the product of what I write in my notes. Let's take the product of P3R cross R2. Okay, so these are both vector spaces over R, so it makes sense to take their product. What kind of vectors live in here? Well, it's a product of two vector spaces, so it's just pairs where the first element is a polynomial of degree less than or equal to 3. The second element is a vector in R2. Right, so it contains stuff like 2x squared minus 3x plus 5, comma, 1, negative 1. Right, that's an element of the product. Any polynomial of a degree less than or equal to 3, and then a vector in R2. And addition just happens component-wise, right? So if you take some vector like this, and you add it to some vector like this, 3, 5. The definition of addition is you just add, in the first bit you add in P3R, so there you get x cubed minus x minus 2. In the second bit you just add in R2. Right, scalar multiplication is similar. So it really is, you just sort of just write the vector spaces next to one another. And this example is meant to illustrate the fact that there's of course no way to add a polynomial to a vector in R2. There's no notion of adding x minus 3 to 1, 2. Right, so I don't want to define these things as sums of things between these elements as I did in the sum. Here the addition only happens component-wise, so you always know how to add things. Let's look at another example. Let's consider the product R2 cross R3, R2 times R3. Okay, so what do elements of this look like? So this contains elements where you have V comma W, where V is in R2 and W is in R3. Right, so they look something like, right, the first vector like V1, V2, the second vector would be like W1, W2, W3, right? Where all these things are real numbers, this is what elements of this vector space look like. Okay, well, so what does this vector space seem like? It seems a lot like R5. Because essentially it's just a list of 5 real numbers where you add component-wise and you scale and multiply into every component. Right? So the answer to this question is technically not, right? Because R5 consists of vectors that look like V1, V2, V3, V4, V5, where they're all real numbers. So it's just an issue of parentheses, kind of. It's an issue of how you're viewing these things, right? In R5, you view the element as a 5 tuple of real numbers. In R2 cross R3, you view things as a vector in R2, or a pair of things. One is a vector in R2 and one is a vector in R3. Okay, on the other hand, they are pretty much the same in that they behave the same. The only thing that you're doing is just sticking some parentheses in or you're pulling some parentheses out, right? So really, what's the notion that we should be discussing? We shouldn't be discussing equality, but we learned that what we should be discussing is a concept of isomorphism. Okay, there's an isomorphism between these two vector spaces, right? So R2 cross R3 is isomorphic to R5. And remember, that just means that there exists a bijective linear transformation between them. Right? What you do is you just take a vector in R2 cross R3, and you just map it to just this 5-tuple in R5. And you just check that this is a linear map, which is adjective and surjective, and therefore it's an isomorphism. So these are isomorphic vector spaces. Okay, but if you're talking to like a professional mathematician, they might say something like that these two vector spaces are equal, but that's sort of just an informal way of talking. And since this class is one in which you learn concepts for the first time, we should be really precise. And once you're so good with precision that is automatic, then you're allowed to become more informal. Okay, here's a question for you. What is the dimension of a product? Okay, well, this previous example, we took a vector space of dimension 2 and a vector space of dimension 3, and their product was a vector space of dimension 5. So I think a reasonable guess here is that the dimension is the sum of the dimensions of the VIs. And this is true. So I'll state it as a proposition and then give at least a proof sketch. So suppose that V1 to Vm are all finite dimensional vector spaces. Then the dimension of the product is equal to the sum of the individual dimensions. Right, so in particular, I should mention that this says that the product is finite dimensional because it has a dimension which is a finite number. Okay, and the proof, just a sketch. You can fill in the details. How do you show that something has a given dimension? Well, you just show that it has a basis with the correct number of vectors in it. How do you do that? Well, you just take bases for each of the individual VIs. Right, so pick bases for V1, for V2, up through Vm. And then if V is a basis element, say of Vj, right? So let's say you have a basis element of V4. What you do is you just consider the vector 0, 0, 0, V, 0, 0, 0, where this is in the jth slot. Okay, so I put in the fourth slot because I said, imagine that's a basis element of V4. So you just check that, right? So now you take all possible vectors. You have a basis for each of these spaces. You just stick the basis element in the correct slot and you put zeros everywhere else. So you've got a whole big collection of vectors. You check that this set is linearly independent and spans the product. And how many of them are there? Well, in the jth spot, I need to pick dimension of Vj vectors. So there's dimension of Vj of these ones. In the first slot, there's dimension of V1 of those. In the second slot, there's dimension V2 of those. And so you just have to, when you take those all together, you just have to add up the dimensions. Okay, so all of these together form a basis of the correct length, the sum of the dimension of the VIs. So since we have a basis of the correct length, this shows that That's the dimension of the product. Okay, so what we've discussed so far is that you can take the product to build a bigger vector space out of any vector spaces you want in a very natural way. It's a vector space, and the dimension of the product is the sum of the dimensions of the individual components. And we said that the motivation for this definition is because if you take two unrelated vector spaces, then there's no way in general to add something from V1 to something from V2. But what if for these vector spaces, what if you chose to take subspaces of a common vector space so that you were also able to take their sum? In that case, if you have a bunch of subspaces of a common vector space, you could take their sum, that's some vector space. You could take their product, that's some other vector space. And a good question is, how are these two things related, if at all? Are they the same thing? Is one of them bigger than the other one always? So that's the question that will motivate the next result. So, whoops, it's a proposition. Okay, so let's now suppose that U1 through UM are subspaces of a common vector space V. In other words, I could take their sum, that gives me a subspace of V. I could also take their product, that gives me a new vector space. What's the relationship? Well, let's define a linear map called gamma that goes from the product to the sum. What is it defined? How is it defined? Well, I need to tell you what gamma does to an element of the product, but an element of the product is just an M tuple where each UI comes from UI. This thing, I guess I should say equal, this thing maps to just the sum of these elements. But this sum is defined because each of these UIs is an element of a subspace of V. So these additions can happen in V. Okay, so I will not prove that this map is linear, although it's not difficult to show that this is linear. You just show that it obeys addition to scalar multiplication. So you always get a linear map from the product to the sum. We'll discuss a little bit more about this, but this proposition says that this sum is direct if and only if gamma is injective. Okay, and the proof here is actually very, very clean. So like I said, you should check that gamma is a linear map. Okay, but once you know that, then gamma is injective if and only if the null space is trivial. That's by a result that we proved. What does it mean to say the null space is trivial? It means that the only thing that goes to 0 is the 0 vector. So if U1 plus U2 plus UM equals 0, this implies that this is the 0 vector, right? Maybe I'll put an if and only if to this whole statement, right? So to say that the null space is trivial means that if something adds up to 0, in other words, if something, this is gamma of U1 up through UM. If that's 0, then the thing that you plug in was 0. In other words, all of the U's are 0. Right, but this says that the only way to write 0 as a sum of something from u1 plus something plus u2, etc., is to take all things to be 0. And way back when we defined the direct sum of vector spaces, we said that this condition is equivalent to the sum being a direct sum. If the only way to write 0 is 0 plus 0 plus 0 plus 0 plus 0, so this was by, in the notes, it's theorem 22. This is equivalent to the sum is direct. It's a direct sum. Okay, one thing that I didn't talk about in this proof because I didn't need it is that this map gamma is definitely always surjective, right? Because the direct sum, the sum, this is defined to be all sets of elements that look like this, which just means that you need to be able to take anything from u1 and anything from u2 and anything up from um. But of course, in this map, it comes from the entire product, which means that you are allowed to take anything from u1 and you're allowed to take anything from u2 and map it over, right? So this map gamma is always surjective. You always get a surjective map from the product to the sum. This proposition says that, oh, also, if it's injective, then it's a direct sum. So if the sum is a direct sum, then you actually get that the product is isomorphic to the sum. So in other words, right, so this means that if you actually have a direct sum, this will be isomorphic to the product as vector spaces, where the map is given by, I guess in this case, the inverse of gamma. I probably should have written this the other way around. Okay. Notice here that this proposition, everything on this page here, I'm not making any assumptions about the dimension of any of the subspaces or even of V. Right, so I'm not assuming finite dimensionality. This result is always true. Everything on this page is always true. You always get a linear map from the product to the sum. It's always surjective. And the sum is a direct sum if that map is injective. But if in addition you have finite dimensionality, then you have another tool to try to understand these vector spaces, right? In that case, you have the dimension, which you don't have in the infinite dimensional case. And the next result, which probably I can still fit on here, refers to this situation. So now suppose that V is finite dimensional, which I didn't assume previously. And un through um are all subspaces of V. Okay, which means also that they are all finite dimensional. Okay, then this is a direct sum if and only if the dimension is the same as the sum of the dimensions. Okay, quick proof. Right, so let me backtrack a little bit. We know that that's the dimension of the left-hand side. That's the dimension of the product, right? Because we just proved that. So if the sum has the dimension that you expect out of the product, then it's a direct sum because it must be isomorphic to the product, as in the previous remark. That's all this is saying. Okay, so the proof is, well, we said that gamma is surjective. So by the rank nullity theorem, what does the rank nullity theorem say? It says that if you take the dimension of the domain, it's equal to the dimension of the range plus the dimension of the null space. Right, so the dimension of U1 cross UM equals the dimension of the range. But if it's surjective, which it always is, that's the dimension of the sum plus the dimension of the kernel, the null space. But we just said that the sum is a direct sum if and only if gamma is injective, which means it's a direct sum if and only if the dimension of the null space of gamma is 0, which means it's direct sum if and only if these first two numbers are equal because the third number is 0. And so the sum is direct if and only if the dimension of the null space is trivial, because that's what we just proved, which happens if and only if the dimension of the product equals the dimension of the sum. But we just proved earlier that this was the sum of the dimensions. So altogether, you get that the sum is a direct sum if and only if the dimension of the sum is equal to the sum of the dimensions. Okay. So the product is, I don't know, maybe the most common way to put together a bunch of vector spaces. It's definitely the one that you need to know the most. I would say the sum is probably the one that you need to know the second most. When you take, but they actually coincide in the direct sum case. That's sort of the point. Okay. So like I said, we won't be talking about quotients. So that's just a half chapter just on products because they're very useful. But now we're going to move on to what I think is going to be maybe a more interesting, maybe more challenging, more abstract section of the textbook, because probably maybe this is one of the first sections where everything is kind of very new. Okay, so what's the setup? Believe it or not, we're going to let V be a vector space. Okay, and one thing that we saw is that the linear maps V to V from V to itself were important enough that we even gave them a name. We called them the operators on V. These are called operators. And when you study the operators of a vector space, you can learn a lot about the vector space. Another very important set of linear maps are the linear maps from V to the field. Okay, so I'm just stating this as a fact. These end up being extremely important. The maps from a vector space to itself are important. Those are the operators. The maps from V to the base field are also very important. And so we give those a special name. Those are called linear functionals. Definition. A linear functional on V is a linear map V to F. So we're just giving them a special name because they're so important, right? They are just linear maps to the base field. Okay, but we use the notation. Okay, so your book uses V prime, but you'll also commonly see in the world V star. So I will stick to primes most of the time unless the star is clear for some reason, which we'll see in a second. And this is just the set of all linear maps from V to F. And this is called the dual space of V. Okay, so this set of linear maps, that's what we call the dual space of V, or maybe you might call that V dual. Okay, so first things first, let's see some examples. Okay, so let's fix an element C1, C2, up through Cn in Fn. Then for each element, we can define a linear functional, an important one. Let's call it phi. So what's a linear functional? It's a map from the vector space to F. And what we'll do is we'll say that phi of a vector in Fn just returns the linear combination of the x1 through xn in terms of the C1 to Cn. Okay, so here, each of the C's and each of the X's is an element of F, right? Because I plugged in an element of F to the N, which means that each of the X's are an element of F. Okay, so to be even more concrete, let's give a more concrete example. You can consider the vector 3, -2, and R2. Then the functional phi sends the vector xy to the vector 3x minus 2, sorry, to the number 3x minus 2y. Right, so like phi of 1, 0 equals 3. Phi of 1, 1 equals 1. Right, phi of 0 pi equals -2 pi. This phi is a map from R2 to R. So it's an element of the dual of R2. Right, phi here is in R2 dual, the dual space to R2. Okay, let's see some more examples. Here's one that maybe you can believe is important. So the linear map, which I'll call J, instead of polynomials over R to R. Right, so this will be a linear functional because it's a map from the vector space to the field. But how am I going to define it? So what J does to a polynomial is it returns the definite integral of P from 0 to 1. Right, so I think we even discussed that this was a linear map between these two vector spaces. But since that second vector space is just the field, we can consider this a linear functional on P of R. So this is a linear functional. So J is in the dual space to P of R. Okay, so this seems like it's a pretty natural linear functional, right? You plug in a polynomial, it tells you something about a polynomial. It tells you the area under the curve between 0 and 1. It spits out that number. Maybe let me give you an even more familiar linear functional. So let's call this EV3 from PR to R, where what it does is it just evaluates every polynomial at 3. Right? So if you take this, you apply it to a polynomial, it just evaluates the polynomial at 3. Right? So more concretely, if you take the polynomial x squared plus 1, it returns 10. If you take the polynomial x cubed minus 2, it returns the real number 25. So this linear functional, this linear map, just evaluates a polynomial at 3. This is also an element of the dual space of the polynomials. Okay, so hopefully these two examples show you that linear functionals will appear all over the place in mathematics. There's tons of things that you can frame in terms of linear functionals. So the goal of this section is try to understand these dual spaces. First results. So let V be a finite dimensional vector space. Then V prime is also finite dimensional, the dual space, and their dimensions match. Okay, so one nice thing is if you take the dual space, you get a vector space of the same dimension. Okay, and we actually already proved this. So we proved that if V and W are finite dimensional, then the dimension of the set of linear maps from V to W is the dimension of V times the dimension of W. So this means that the dimension of V prime, that's the dimension of the linear maps from V to F, which is the dimension of V times the dimension of F, but the dimension of F is just 1. So it's just the dimension of V. Okay, but once you know that it's finite dimensional with the same dimension, you should ask, what is a basis for the dual space? What is a basis for the dual space? And of course, there will be lots and lots and lots of different possible bases for the dual space, right? In general, vectors have tons of bases. I guess everything except for the zero vector space has infinitely many vector spaces. Sorry, infinitely many vector space bases. Here's the one to know, though. Okay, so suppose that V1 up through Vn is a basis of V. Okay, so let's start with a basis for my original vector space. I'm now going to construct a basis of the dual space that's related to this basis of V. Okay, then the dual basis right? So this basis will be a basis of the dual space, but it is related to these V's. So you start with a basis for V, you will obtain a dual basis for V dual. So the dual basis is the list, I'm going to call them phi1 up through phi n of elements in V prime. How are they defined? Each phi j, right? It's in the dual to V, that means it's a map from V to F. So it's defined by, okay, well, to understand a map from V to F, you just need to know what it does to a basis of V. So here I'm just going to tell you what it does to a basis of V. It sends Vk to either 1 or 0. It sends it to 1 if k equals j. It sends it to 0 otherwise. Okay, so this, I think, is, now we were like jumping up levels of abstraction. It may be a bit confusing. You may need to think through the definitions and the proofs and the problems kind of a long time to understand these things. Okay, so I don't think it's an easy thing because you've never thought about the dual vector spaces before, but they're extremely important in mathematics. Okay, so one thing to note is the notation that you choose helps to remind you of what's going on, right? So I'm using phi's for elements of the dual because phi is often the name of a function in mathematics, right? I'm using v's as elements of V because those things you think of as vectors. Of course, V dual is also a vector space, right? So these phi's, you could also say that they're vectors, right? Because they're in the vector space V prime. But the way that you think about them is you think of them as linear functionals. You think about them as functions from V to F, right? Which is why I've written this phi j of Vk. You can plug in Vk's into these phi j's. Like I said, these are n different linear maps, but a linear map is determined by what it does to a basis. So here I've just told you phi1 sends V1 to 1 and sends all the rest of the vectors, all the rest of the basis vectors to 0. Phi2 sends v2 to 1, and sends all the rest of the vi's to 0. Okay, so here I truly have defined a bunch of linear maps on V, exactly n of them. Okay, but like I said, I know that this is kind of an abstract thing, so let's look at an example. So consider the standard basis. E1 up through En of f to the n. Okay, then, well, we said that the dual basis to the standard basis is phi1 up through phi n, and it's defined by what phi j does to ek is it returns 1 if they match, 0 otherwise. But that's just what the phi j's do to a basis. What does phi j do to it? Okay, I guess what does phi j do to a general vector in Fn? What is phi j of x, where x is a vector in Fn? Okay, well, if x is just any old vector in Fn, it looks like this. Well, that means that you can write x as x1 e1 plus x2 e2 plus xn en. What does phi j do to x? Well, you just apply it to this right-hand side, you break it up over the sum, and you pull out the scalars because it's linear. Right? So this becomes x1 phi j e1 up through xn phi j en. That's a number. Okay, but most of these phi j's are 0, except at the jth spot, right? So in the middle here, there's going to be an xj phi j ej. That phi j ej will give you 1. So what this in the end becomes is xj. So what does phi j do to a vector? It just pulls out the jth coordinate. So if you have the dual basis, the standard basis, the elements of the dual basis pull out the jth coordinate of a vector in Fn. That's what those linear functionals do. Okay. Let me just mention, though, that when I define these things, I called them the dual basis. You start with the basis, you get a dual basis. But we never actually verify that these things give you a basis of the dual space, which is a problem that we need to fix right now, right? So if V1 through Vn is a basis of V, then the dual basis, right? And again, the dual basis depends on the basis of V. But this is the basis of V dual. So that justifies the term dual basis. It's the basis of the dual space. Okay, so how can we prove this? Well, these are definitely n elements of the dual space, and we know that the dual space has dimension n. So we can just check that these phi 1 through phi n are linearly independent, because any n linearly independent elements in a vector space of dimension n are automatically a basis. We proved that. So since we know that this dual space has dimension n, it suffices to show that the phi 1 up through phi n are linearly independent. How to show that a set of vectors is linearly independent? You suppose that you have a linear combination which equals 0, and you show that it's a trivial linear combination, right? So let's suppose that a1 phi 1 plus a2 phi 2 through an phi n is 0. Okay, but where the heck is this linear combination happening? this linear combination is happening in V dual, right? The A's are scalars, the phi's are functions from V to F. So this zero, this is the zero of V dual, which means that this zero is the zero function on V. The zero vector here is the function that sends every vector in V to zero. Which means that I can apply the left-hand side and the right-hand side to any vector I want in V. Okay, so apply these functions to, let's just say V1. Okay, well, A1 phi 1 plus AN phi n evaluated at V1 has to be the same thing as 0 evaluated at V1, which is the number 0. Right, so this 0 was the 0 functional. This 0 is the number 0. Maybe I should underline it in a different color. This 0 is the number 0. Okay, well, what is the left-hand side of this? Well, this is the sum of a bunch of functions of a bunch of linear maps. So what you can do is you plug in V1 to each of the functions, and then you add up the result. Right, so here you get A1 phi 1 V1 plus A2 phi 2 V1 up through AN phi n V1. But since this was the dual basis, phi 2 of V1 is 1, but phi 2 of V1 and phi 3 of V1 up through phi n of V1, those are all 0. So this is actually equal to A1. Right, so this computation shows that A1, this coefficient, has to be 0. But then you can apply the function to V2 to show that A2 is 0, V3 to show that A3 is 0, up through Vn to show that An is 0. And so similarly, A1 equals A2. These all must be 0 by evaluating. I mean, you could just, instead of putting V1 here, put Vj, which I think is what I did in the notes. So this shows that the only linear combination of the dual basis that gives you the 0 functional is the trivial one. In other words, the phi's are linearly independent. In other words, they form a basis of the dual space. Okay. So if you're a little bit confused, that's okay. Everybody in the world, I think, is a little bit confused when they first learn about dual vector spaces. But it's an extremely deep topic with connections all throughout mathematics. So you just have to, anytime you learn anything, actually, anytime you learn anything that's even a little bit challenging, it's very, very hard at the beginning. Even for me, right? Like I said, I took a lot of math classes. I've read a lot of math things, and even not math, but nowadays mostly math. So I've been very, very confused by so many things. But you have to power through, and eventually, when you really learn it, then you can say, oh, that's a lot easier than I used to think it was. Okay. Plus, I'll give you lots of homework problems, so I'll force you to think about it. But here's an interesting feature. So an interesting feature of dual spaces, and it's a very natural one, is if T is a linear map from V to W, then there is a natural linear map from the dual space of W to the dual space of V. Okay, so let me motivate this. How can I possibly say there's a natural linear map from W dual to V dual? Well, okay, so what is W dual? W dual is all of the maps from W to F. And V dual is all the linear maps from V to F. Okay, so you can think about a linear map from W to F as like some kind of arrow, like this. Okay, now, if you have a map from V to W, then for every element of W dual, which means that for every function from W to F, I claim that you can get a natural function from V to F. Okay, so if phi is a function from W to F, how can I possibly get a function from V to F? One thing you could do is you could just take T, map from V to W, and then take phi to map from W to F. So that gives you a map from V to F. So for every element of W dual, if you precompose with T, you get a map in V dual if you start with a map from V to W. Okay, and this map from V to W, giving you a map from W dual to V dual, that map from W dual to V dual is called the dual map to T. So let's define it. If T is a linear map from V to W, then the dual map of T is the linear map. So we use the notation T prime. That's T, you read that T dual. So it's a map from W dual to V dual, defined by what? Okay, well, T prime is a map from W dual to V dual. So we pretend that phi is a map in W dual. You need to spit out a map in V dual, but what you do is you precompose with T. So it's phi of T. And this is for all phi in W dual. Okay, and again, the picture is just the one that I've drawn above, right? So phi goes from W to F. To each phi, you just compose the map T to F. And this part, the squiggly arrow, this thing is T dual. It just precomposes with T. Again, kind of an abstract thing. And you need to think hard about these things before they become ingrained, where you're used to thinking of things as functions versus things as vectors, etc. Okay, but the thing to notice here is that when you take duals, not only, so for each vector space, you get a dual vector space. Now we're saying for each linear map, you get a dual linear map going the other way. Okay, so in your mind, you can think of all of the vector spaces over F living in some world of vector spaces. Right, so you have all these different linear maps. Sorry, all these different vector spaces over F, and they're all living in some world, and there's some linear maps between them. Right, so the world consists of vector spaces and linear maps. Now for each vector space, you can take the dual. That gives you another vector space. Also for each linear map, you can take the dual, and it gives you a map between the dual vector spaces, but the arrows have flipped around. So you can think of maybe some kind of mirror or something, right? So you have an entire world of vector spaces, linear maps, but there's this flipped world of all the duals of those vector spaces and all the duals of those linear maps, and all the maps are going in the opposite direction. Okay, so if you go on to take more mathematics, you realize that what I'm saying is actually, there's a really precise way to say what I'm talking about. The thing to remember here is just that we now know how to take duals of vector spaces. We also know how to take duals of linear maps. So the last one we'll do today, let's look at some examples of dualizing some linear maps. Okay, and for these examples, I'm going to want to reserve prime for differentiation. So I'm going to denote duals by using asterisks. Okay, so let's consider the linear map D from the set of polynomials to the set of polynomials given by differentiation. Right, so in other words, D of a polynomial just spits out the derivative of the polynomial. Well, this is a linear map from one vector space to another, to itself, but that's to another, which means that we should be able to take the dual of this map to get a dual map from the dual of P of R to the dual of P of R. So we want to understand that's terrible. We want to understand D dual, again, I'll use asterisks, from the dual of P of R to the dual of P of R. So this is like the flipped world. Really, this arrow is going the other way, but the domain and the range are the same, so you can't tell. Okay, well, in order to understand this dual map, I need to take an element of the dual. I need to take an element here and see what D dual does to it. But we already know two elements here, right? So there's evaluation at 3 that lives in the dual space. Also J, the integration from 0 to 1, that lives in the dual space. So let's see what happens to them when you map them over using D dual. Okay, so what is D dual of this linear functional evaluation at 3? Well, how is it defined? Well, this thing is going to be an element of the dual space to P of R. So this thing should be a function that takes in a polynomial. So by definition, what is this function evaluated at a polynomial P? Well, by definition, what it does is this. If you evaluate D dual on a polynomial, sorry, on a functional, if you evaluate D dual on a functional, it takes the functional, but it composes with D. So what this does, it does evaluation at 3 of D of the polynomial P, which is just evaluation of 3 of P prime, because you differentiate it first, which is just P prime of 3. Okay, so if you take this differentiation map, what its dual does to the evaluation at 3 functional is it gives you a new functional, which is supposed to, which just evaluates the derivative of P at 3. Right, so this is the functional which maps P to P prime of 3. That's what D dual does to one element of the dual space of P of R. Okay, let's consider another element. What is D dual of our integration functional? Okay, well, what does it do to a, right? So this thing, again, should be a functional on the set of polynomials. So what does it do to a polynomial? Well, it's supposed to do exactly J of D of P, which is J of P prime, which is the definite integral of P prime of Z dz. Which also we know, I mean, this is a polynomial, everything in sight is infinitely differentiable, etc. By the fundamental theorem of calculus, this is P of 1 minus P of 0. Which means that this functional, what d-dual does to the functional j is it gives you the functional that maps p to p of 1 minus p of 0. Okay, so that's an hour. I would say the first half of today where we talk about products, you should feel comfortable with probably relatively quickly. But the stuff on duality, I expect many of you, it will take time to become comfortable. So like I said, I'll give you homework problems, but it's one of these things that you need to continue thinking through before you'll become comfortable with it. And on Friday, we'll continue discussing duality. All right.